You've already heard about dense hydrogen in 2 talks at least, so I'm going to go through this part rather quickly. It's a very interesting system to study, both because connections to other areas of science, mainly in astrophysics, engineering things like inertially confined fusion, and now superconductivity of hydrides is a big area. I'm more interested in the fundamental physics, what phases are stable. I'll come to that in a second. But the other reason I'm really interested is it's really a benchmark for simulation. Can we do it? Can we do the first element? If we can't do hydrogen, I mean, come on, you're going to be able to do copper oxide? Probably not. So, and it's simple in the sense there's no core states, and you don't have to worry about pseudopotentials, which is a blessing. However, the protons are quite quantum mechanical, and you just can't assume they're classical and expect to agree with the experiment, but that's something we actually know how to treat. Here, the phase diagram referred to this figure quite a bit. I mean, this is on an astrophysical scale of, does this work here? Oh, there we go. You have to have small fingers. You have logarithmic pressure and logarithmic temperature here. And so, the hydrogen laboratory is down here at low temperature and low pressure. So this is our experimental world down here. Okay, you have fluid hydrogen, and then eventually you have a plasma up here. So the interest in the talk is going to be at high pressures and not so high temperatures. And the other thing that's important for this talk is what the Fermi level is. That's the Fermi temperature, is a line that goes like that. And so we're going to be below that. So in a way, the electrons are degenerate. That is, they're pretty much in the ground state, not entirely, but the protons are not. And so referring to this diagram, maybe I should just refer to the question is, how much of this phase diagram do we understand? Like the classic, it's called the holy grail of high pressure physics, is this little gray box right here, is how do you make a transition at low temperatures from H2 to H? And Ashcroft suggested a number of years ago that all this should be superconducting here. Of course, it hasn't been experimentally found. One of the things that we'll talk about is this funny little line right here, and this is the so-called liquid-liquid line. It's not well, I'll talk more about it, but its status, you see, is it there or not? It doesn't have to be there. You could shrink this line down to a point, and then you would just go from the H2, molecular H2, to liquid hydrogen, that is atomic hydrogen. You don't have to go through a phase transition. This critical point here could lie on the solid line. And so those are some of the physical questions that we are interested in. From the point of astrophysics, the important thing are detailed properties under extreme condition. If you want to model Jupiter and Saturn, understand what's inside them, then you have to know not just roughly Hartree-Fock level, what is hydrogen, you need to know to 1% accuracy what are the properties. And so what about experiment? Well, really nice experiments are these so-called diamond Anvil experiments, where you take 2 diamonds and you make a little cavity and you compress it. These are tabletop static experiments or dynamic experiments, but they're limited in pressure and temperature because the diamonds break, and hydrogen under these conditions it attacks the diamonds, right? It goes into cracks and makes them break at a certain point. Like this would be 100 GPa, on the order of 300 or 400 GPa. Of course, every year experimentalists push the boundaries, right? And they actually go up in this direction too. The diamonds break too. They really would like to be at room temperature and below, but if you treat them very carefully, maybe you can go up to 500 Kelvin, or in a dynamic experiment where you pulse a laser beam in there, maybe you can go up to 2,000 degrees before the diamonds break. The other kind of experiment is the shock experiment, where essentially you take a little capsule, and Ray talked about this a bit, and you hit it with some enormous energy, either a bullet or a laser or something else, and you generate what's called a Hugonio, and that's the locus of points on this diagram that you can reach by hitting it, starting from this point right here. You start down here because you want to be in cold as dense as you can. Shown here are if you drill a hole in Jupiter, you would follow a trajectory like this, theoretically. Of course, we don't really know. Okay, so what can we do theoretically? Of course, with DFT, you can do everything, but as Ray showed in his talk, that the results depend on the functional a lot. So with quantum Monte Carlo, what can you do? Well, the diffusion Monte Carlo, which is what we started it is of course a zero temperature method. So you're down here somewhere, right? You can look at the solid phases, that's true. There's a problem with the separation of electronic and protonic timescales, but otherwise you can do a good job here, except for, like Matthew said, the finite size effects. A while ago, we started doing path integrals on this system. You're starting essentially at 1,000,000 degrees when you do path integrals, that is up here, and you're working your way down. And we found a sort of a practical limit of something like 1/10 of the Fermi temperature. That's why we have this yellow triangle. It's hard to get reliable results down here, although there's no mathematical reason why it should be that way, but eventually we got tired. But the real, our interest is in this region, the warm dense matter region, and that's what I'm going to talk about today, these simulations in this region, down to rather low temperatures, 200 Kelvin or 100 Kelvin, and also up to rather high temperatures. So we're going to make what's called the Born-Oppenheimer approximation, but a lot of times people think Born-Oppenheimer means classical protons. No, we have quantum protons. It's just we're assuming the electrons are in their ground state, and then the potential that the protons see is parametrically, is related to the electronic ground state. So in that sense, we're doing Born-Oppenheimer. So this was our dream, and when I say our, it's Carlo Pierleone from Rome and Marcus Holtzman from Grenoble and myself started working on this a long time ago. And the dream was, can we do the whole thing with quantum Monte Carlo in this warm dense thing? That was our goal. How far can we get? And so basically, both the motion of electrons and protons is based on quantum Monte Carlo. So this would give us a quantum Monte Carlo level of accuracy. Either way, hydrogen is a lot easier to do with quantum Monte Carlo than the things like Matthew was talking about. You get a lot more correlation out of it. It's those core electrons and things cause problems, right? And so we're not going to use pseudopotentials at all, and so we don't have basis set limitations. We have a do things continuous time. We want to treat solid, liquid, plasma in thermal equilibrium, with a caveat I said already about Born-Oppenheimer separation. So essentially, the electrons we're assuming are in the ground state, although sometimes we do calculations where we excite the electrons, but normally they're in the ground state. And we want to calculate unbiased observables. So we don't want this mixed estimator bias of things besides the energy. We don't just want to calculate energy. We want to calculate momentum distribution, pressure, correlation functions, and so forth. Yes?
Okay, quick question. So you said the electrons are in the ground state. So, but when you're doing finite temperature, and
the protons are moving around, and so you assume that electrons have come into the ground state of wherever the protons happen to be.
I see. So the protons are at finite temperature, but the electrons are basically zero temperature.
Yes, that's right. That's right. Exactly. And I'll say, to do these problems, we want to have a supercell periodic boundary conditions with on the order of hundreds of protons. This is kind of a limitation. If we wrote the code today, we could maybe do bigger systems, but the way it's kind of hardwired in to do not too big of systems because of backflow effects. And so we do have approximations beside that. The other one, of course, is the sign problem thing. We do fixed phase. It's like fixed node with complex wave functions. But we do have backflow wave functions so that we have improvement of that. And so basically my outline is that I'm going to turn the talk around and show you the kind of things we can calculate, the physical problems we can calculate. And as I have time, I'm going to talk about some of the methods that we have developed to do this. Because we had this goal, and I'm one that believes strongly that when you develop methods, you should be trying to solve a hard problem, and then you can develop the methods in terms of that problem you're trying to solve. So first I'm going to talk about this Hugonio. This is kind of like our bête noire. The Hugonio, by the way, there's experiments. This is the one somewhat clean experiment that they can do. They take hydrogen and they hit it with a shock wave, right? Various kinds of shocks. And they generate data points along here depending on how hard they hit it, how big their hammer is. And these are the points. Okay, so this line that I kind of drew by eye is the experimental results from Sandia, actually. And our points are these blue and green. The green are very older results, but they're pretty close to our new results, except for this point right here. And we understood that our molecule, this is the molecular phase down here, and we understood that our molecules just were not, in 2015 when we did this, were not coming into equilibrium. And so actually, the reason why this is a bête noire is that it's a huge cancellation between the pre-shock and post-shock that you're doing. And it's a hard calculation, and it's a hard experiment. And the experimentalists put error bars here. But, you know, error bars are only on the known unknowns, right? That what they think are their experimental limitations. And there are lots of other limitations that they don't know how to put limits on. So, you know, you have to take it somewhat with a grain of salt. But, you know, this point, we don't agree, it's true, but it's not that many standard deviations away. And we know that we have biases in our calculation, and so, you know, it doesn't, we think this is a pretty good agreement, okay, so and it's not perfect. Okay, so the next thing I want to talk about is this liquid-liquid transition, which is this little purported line. This was actually invented by Landau and Zeldovich in 1943 in the Soviet Union. An interesting time, but in mercury, not in hydrogen. But it, you know, it had a kind of the question is, like, if you go inside Jupiter, you come to something like the ocean, where above the level of the transition, you have molecular liquid, and below it you have this metal of metallic hydrogen. Is it there or not? And if this line isn't here, it would just be be like clouds, right? It would just go continuously from insulating to metallic state. And it would have been a dispute because there wasn't really a method to examine this, because this is a difficult problem. I mean, you have molecular dissociation, you have an insulator metal transition, and you have thermal effects, right? And in 2010, we think we did the first credible calculations showing it. And these are 4 different panels, show 4 different properties as a function of pressure. This was all at 600 Kelvin. But here is the jump in volume. And it's a really small effect. Actually, we published a paper in one of our first papers in about 5 years earlier. And we missed this entirely, because if you have a coarse grid and not enough computer time, you don't see it. But in 2010, Miguel Morales saw it, and we saw it in the disappearance of molecules. This is the molecular peak here. And this is this is the conductivity here. And so it's both an atomic molecular transition and an insulator metal transition. It's not two separate transitions, as some people think. And just to respond to what Matthew said, here's an example of quantum Monte Carlo spontaneously showing a phase transition. There's nothing in our calculation that forces it in one phase or the other phase. It just spontaneously and without much hysteresis goes from one phase to another.
Is there a fixed phase approximation?
Yes, there is.
Both phases can be described with the same oval surface density.
Well, in both phases, in this case, we're doing DFT for the orbitals. But don't forget that transition is in the protonic degree of freedom also, and they don't have any phase. And so
they're Boltzmann-ionic.
Yes, they are Boltzmann-ionic because the statistics would be only relevant like 10 Kelvin, and we don't go that low.
And your electronic state is...
I'm going to get to the under the hood part where I describe all that stuff. Right now I'm just giving you results to see what kind of things that we're doing. We were very happy when 3 different experimental groups looked for this transition. And this was the culmination in 2018. And I think Ray may have showed this too. Our results are this green thing. And this was the Livermore NIFT result, which is, I consider, almost on top of it. These are incredible. These are even much more difficult than the Hugonio experiments. So you have the Sandia results that doesn't show them very well, but these points right here, they're way off, and it's not known to me why they are off, but it's because it's such a difficult experiment, and you have to do hydrodynamic calculations in order to understand the experiments. It's just not like you do a measurement of it. It's like you have to model the whole double shock dynamics and so forth of not only hydrogen, but aluminum and different things. And these are the Harvard results from Cervera's group. We understand perfectly why they don't agree with us. It's just simply because the photons that they're using in their laser are not zero energy photons. There's a finite energy, and they're just seeing how much absorption the system is as you heat it up. And once the gap closes to where the photon energy is, it changes. If they had lower energy photons, this line would move over to where our line is. So we've done optical calculations that show that that's correct. So we kind of understand that. Here's an example of a prediction that we've been able to make with our code. And here's the band gap. These are optical measurements at low temperature, like 100 Kelvin, okay, and 300 Kelvin. And our points, are this line right here. And basically the experiments are close. They're not perfect. I mean, these band gap calculations are more difficult. They have much worse finite size effects to deal with. But we show the overall trend, namely the band gap in solid hydrogen closing as a function of pressure. And they think they're up to 400 GPa, that is 4 million atmospheres. And it's going to close soon. So this would be the estimate of when you actually go to atomic hydrogen, when you get an intercept here. So this is it. Now, about 3 or 4 years ago, Carlo kept saying, well, our coupled electron ion Monte Carlo solids do not melt when the experiment does. This is supposedly the experimental melting curve right here, temperature versus pressure. And he was getting melting up here at almost twice the temperature. So this is when we started doing machine learning, because we were worried that a solid liquid transition would just be too slow. I mean, we can only do on the order of 10,000 or 100,000 steps. That's our computer budget. And maybe it just hadn't come into equilibrium, maybe a lot of different things, okay? So anyway, here's the result of our machine learning calculations. there's some things here. PBE means other people's DFT ab initio DFT. Our calculations using quantum Monte Carlo machine learned potentials, the best one is this kind of light purple shade here. It's still way above experiment. Now, then we start looking into the experiment. Experiment consists of a very weak Raman spectral line where the line disappears at this temperature, like 700 Kelvin. The absence of signal is not the signal of whatever. You know what I mean? It doesn't necessarily prove something is true. There could be a lot of reasons why a signal disappears. For example, it broadens out, it moves to a different location out of your range where you can see it because this thing is inside diamond and so forth. So we've hesitated publishing this because we keep checking things, make sure we haven't made a mistake. But I was pretty confident that the solid hydrogen is more stable than it's generally perceived to be true. In fact, we're getting a lot. This is actually solid line. There a paper came out this year showing the phase diagram by these Raman by using Raman spectroscopy. This is what hydrogen probably looks like. It's a much more complicated. You might think hydrogen, you study that in elementary quantum mechanics, that's got to be simple. But it's no simpler than any other material, right? Look at all these possible phases. I mean, you know, they call them 1, 2, 3, 4, but now they have to do like 4' and 1' and whatever, you know. And I'm not sure I believe these lines, but we're actually getting more complicated phases. We're getting different phases, and we're getting a lot of these lines here using our machine learning. But we're just still learning how to do this stuff. And, you know, we get a different phase diagram right now, but okay. But we haven't published either. When it comes out, we'll tell you exactly what we think. So that's the result side of things. And I still have half an hour, okay? So I was going to tell you about what's under the hood. So remember, the goal here is just to do, with quantum Monte Carlo, start with a Coulomb interaction and the massive electron and proton and go from there, okay? And so first of all, the broad overview is what's called Coupled-Electron Monte Carlo. And I'll explain this a little bit, but this is kind of a conceptual picture, is that you have two Monte Carlos going on here. You have the main Monte Carlo is the electronic Monte Carlo, where you calculate the energy. And the energy, and then you have an ionic Monte Carlo, a proton, which could either be a classical metropolis Monte Carlo, or it could be a path integral Monte Carlo. I mean, the more accurate calculations when we have computer time, we would represent these quantum mechanically. But when you do metropolis, you have to calculate energy differences. And we invented something called a penalty method, which I will explain in a few minutes, in order to make this coupling possible. Because you cannot run the electron Monte Carlo so long that the error in the Monte Carlo is zero. You know, it's going to have some error. So you have to have a way to cancel out the bias, because in the metropolis formula for the acceptance, it's a nonlinear function, and every time you have a nonlinear function, you have a bias. Okay, so anyway, now then what do we use for the electronic Monte Carlo? That's the time-consuming part. Well, we use Reptation Monte Carlo, which I'll review in a minute. But in Reptation Monte Carlo, you have a trial wave function, you expand it in a path, and then you project it back on the trial wave function. So it's a projector method, but it's not like diffusion Monte Carlo where you have branching. Instead, you represent a path, and you move the path around according to metropolis. And I'll explain why you do that. But first, I'll explain about the trial wave function. Maybe that was your question. I'm not sure, but you know, you've seen Slater-Jastrow. Everybody knows what that is. Okay, so I have a different take to most people here, I suppose. And I'll explain this, but you know, I want to have simple functions here, and I want to have those functions that do not have to be optimized during the Monte Carlo. I want, for a given temperature and density, I'm willing to optimize things, but as the protons are moving around, I just want to have them to be fixed functions. That is, of course, they depend on the proton coordinates, but I don't want to have parameters in there that have some dependence, okay? So this was in, at some point, we realized we couldn't quite do this and describe the molecular phase, so we had to integrate it with a DFT code, but we made it some changes so that the DFT code was very fast. That was to get the orbitals. Now, originally, I thought backflow would solve the problem, but I was confronted with reality that it would be better to actually have a eigenvalue solver in the middle of it. Okay. So anyway, this is my philosophy. Again, it's based on the Feynman-Katz formula, and I know somebody asked me a question about this, but basically this is an exact formula in certain situations for the many-body wave function. Capital R are the many-finite coordinates. This is an anti-symmetrizing operator here. You take an initial wave function, an initial guess, and you construct random walks starting from this point R, and you take the local energy of your trial wave function at the nth level. Okay, this is an iterative procedure. At the nth level, this is your local energy at the nth level. So this is the residual or the error of your trial wave function right here. If you then construct random walks based on this wave function, and you exponentiate it like this, and you integrate from 0 to infinity, you get the exact wave function. Okay. It's only formally true if this thing is positive, but then the anti-symmetries are fixed sets. Okay. Now, in order to use this in practice, you make what's called a cumulant approximation, which you bring this averaging inside the exponent, right? And it's known that's a good approximation in some situations. And in order to do the time averaging, the integration in time in imaginary time, you just replace it by tau, and you have an expression like this. So, and then, okay, so in practice, what is it? So the 0th order would be a Hartree-Fock wave function, or it wouldn't have to be Hartree-Fock. It could be just a product of any independent orbitals, right? And then what's going to be your local energy? The local energy is just going to be the Coulomb interaction in that case. And so then you do an averaging, and the Coulomb interaction turns into a Jastrow. So that's the origin of Slater-Jastrow. It's not a mystery. And at that point, we take the Jastrow factor as an adjustable parameter, right? And because we don't know how to do this averaging, so we'll say, well, in that class of functions, what's the best thing you could do? If I've used mostly RPA, because RPA is a way of parameterizing it, because RPA gives you the exact small r and large r behavior of the Jastrow factor. Okay. Now, if you do it one more order, which is all I've ever done, you generate 2 more forms. That is, what is the error, the local energy of this Jastrow, Slater-Jastrow wave function? Well, when you act on the Jastrow factor, you get a 3-body term, which doesn't change the node, so you may say it's not so important, but it's there. But anyway, when you act on the Hartree part of the wave function, you get backflow. Now, the thing that's interesting to me, it was always interesting to me, is now we have 3 one-dimensional functions characterizing the wave function, namely the Jastrow, which I didn't put up here, this eta function and the zeta function, right? And so you've reached my goal, a trial wave function expressed in terms of these 3 one-dimensional functions, and you just have to ask what do those functions look like? What is the optimal form? RPA sort of tells you, and actually this Bohm-Pines procedure gives you, Marcus figured out how to do it for backflow and 3-body, gives you analytic forms. And that's why I sort of flippantly responded to the talk yesterday. How many parameters do we have? 0. Not 100% true. Of course, I'm going to do little perturbations here if it improves things, right? But that's still like only a few parameters, like 3 or 4 parameters. And I hope those parameters are density independent and temperature independent or whatever. They're just, they're things that correct these errors. Yeah?
A little confused. RPA for uniform gas.
No, RPA for electron-proton mixture. That's what we use, in fact, for this problem. It's RPA in a certain sense. I don't know, it's something that I learned from a paper by Tony Gaskell and back in the 60s, how to do this. You write out the local energy and K-space, and you drop the one term you can't deal with, and then you solve it for the other terms. Yeah. And it's believed that it has the exact long-range properties, and it also has the exact short-range properties. And somewhere in between long-range and short-range, it's not exact, but
That's for the electron proton.
yeah.
Yeah.
Yeah, and the electron-electron. You do it like a 2x2, 2-component mixture, right?
But it's not exactly electron problem.
No, it is. I mean, it gives you the cusp condition in that sense. That's what I meant. It gives you the electron-proton cusp. And then it goes to the plasmon limit at long wavelength for a metal, yeah.
The cusp you put in, it's not kind of RPA, is it? Beyond that.
Well, the Gaskell procedure gives you the cusp. Yeah, maybe it's a little different than, yeah.
I'm confused about the Feynman-Catch formula. Sorry, the one I remember.
The one it doesn't have this.
You just have potential energy up there, not the whole.
Okay, this is a generalized. I didn't have enough room on the line to put generalized.
What are the paths sampled from?
This is the formula that you use in diffusion Monte Carlo if you're doing forward walking, right? How do you do forward walking? You sit at a point, you generate walkers and that drift with your trial wave function, and then you integrate your local energy out, and that gives you the corrected wave function. So it's exactly that. And so that you may have not noticed this subscript here, which means that you're averaging over paths that are generated from phi n. Right?
So it's the drift diffusion propagator that generates phi n.
Yeah, yeah.
So you also need to confine your sampling to a fixed node.
No.
No.
Okay. That's a tricky thing. And then, of course, we're going off of mathematics into more hand-waving stuff. But suppose I start with these phi n's as being a Hartree that is strictly positive orbitals. Then everything is a probability, and I don't have to do fixed node. And that's the only way you're going to get this backflow, actually, to come out. But you can put the anti-symmetry out at the end of the day, and then you change this thing into a determinant. So, yeah, you don't have to do and this Feynman-Catch formula, if you do it in this order, you don't have to do fixed node. You could have the same formula with fixed node, but then you would have, I'm not sure, maybe it's what you're doing. You'd be anti-symmetrizing a determinant, and it'd be kind of a big mess, I would think. Yeah?
Did I get it right that you're saying that traditional Beck's form only assume from this procedure only if you assume strictly orbital?
Yeah, well, this is a probabilistic argument, and so I want to make sure that I have a probability and not. But you can probably do some sort of analytic continuation. That's what I always thought, to go from the positive case to the complex case, which is, of course, the case we're interested in. I leave that to the mathematicians to figure out how you continue over from that to the other, yeah.
Loosely speaking, this is the interpretation of the backflow as a single trajectory approximation to the Feynman
No, this is an average over many trajectories. That is, you start at a point R, and you start an infinite number of trajectories, and that's what you want to do with that's what the average means.
To me, the backflow is you take a configuration and there's a deterministic mapping from R, I.
Yeah, that's a result at the end of the day of the average. It's deterministic. But I'm saying, how do you come up with that form? And I think this is useful because sometimes you want to add a perturbation, like you want to add like how does the wave function change if I put in an external field? And this tells you exactly how you do it. You construct your wave function without the field, and then you just consider what the average would look like with this perturbation, right? In this case, we're sort of doing, well, anyway. Does that answer your question?
What I heard is my interpretation wasn't correct. I have not.
Okay. Okay. Well, how accurate is this? Well, of course, we don't really know in all cases. Just one time we did this thing where we actually assessed if you can see these little dots here, but we have 5 different configurations here. We calculated the energy and the variance with different types of wave functions. And we did what's called variance extrapolation, namely, maybe you know what that is, and estimate how much lower the energy is. And we figure out the QMC energies are accurate to about 100 Kelvin per atom, that is, referring to what Matthew said. If we had 100 atoms, of course, it would be 100 times bigger, but the error. But hopefully it's all local, and that's a good estimate. But one expects that relative energies are a lot more accurate than this. Most of this, a lot of the error cancels out. Now, the Reptation Monte Carlo is basically, this is the kind of the picture here. Well, this is the mathematics, basically, projector method. But your projector, you expand it into a path of p steps, okay? And so this becomes your wave function, which we parameterize by beta here. You project it by beta over 2, and then, so this is like a partition function for this fictitious system. So this is like the quantum system that you're simulating, which has like p steps. So it's called a zero temperature path integral. It is path integral. It's open, and the only thing that's different with path integral Monte Carlo, in addition to being open, is you start and end with a trial wave function, right? Those are the boundary conditions. And you calculate the energy by the usual way. And you get an upper bound converging to the answer. Typically, we have P is on the order of 100 steps. Now, why it's called reptation, which if you don't know this word, is a word that's used in polymer physics. It means Dijen gave us this name, move like a snake. So basically, you're going to do metropolis, and this is the probability that you're going to do. And the idea is, instead of moving the whole thing randomly, which is kind of inefficient, you just cut off one end and move it to the other end. Because then all of this probability, you don't have to do any calculation. You only have to do a calculation for the new point that you inserted, which is, just like a usual step in diffusion Monte Carlo, right? But you don't have these, the advantages is properties in the middle of the path are pure ground state properties. And so you can calculate, things like pressure. And the other reason we do it is, remember we need to calculate energy differences. We make a movement of our protons and how much is the energy changes. It's a lot easier to formulate this than in diffusion Monte Carlo, because that rejection step in diffusion Monte Carlo is kind of an awkward thing to do. But you can write down a good importance sampling for how do you calculate energy differences. And finally I have to say we do fixed phase. That's part of this H here, is the thing that keeps it away from places where your trial wave function vanishes, right? We're using the gradient of the trial wave function. So that's reptation. The penalty method, as I said before, what the problem we're trying to solve is we don't want to have to compute the electronic energy to, say, 100 Kelvin. That would take too long. We have to do it faster than that. But if we if the energy fluctuates too much, you're going to have a bias if you just use the usual formula. But we figured out how to do this and basically make the assumption that the change in energy, calculate the energy when you move the protons, how does it change, delta E. Assuming that's normally distributed and you know what the variance is, then you can achieve detailed balance by adding a penalty to the usual metropolis thing. This is an exact result. That is, if you knew it's normally distributed and the variance was sigma, you just have to add this to your metropolis formula, the penalty, so-called penalty. This means that you get extra rejections. Even if you go, say, downhill, usually in metropolis, if you go downhill, you always accept. Here, you have to go downhill enough, right? Because you got a little bias. But then you can ask, how long should I run the electronic Monte Carlo? And it turns out, if you're doing things at KT, you sort of want to get your error bars down to only KT. Right? So if you're doing things like molecular dynamics and you have an error in your forces, you really want that error in the forces to be pretty small to be confident in the results. Here we have a kind of a bound. The main thing, of course, is to establish that you have normal distribution and you know what sigma is. You can actually improve this method a little bit by estimating the effect of an error in the error. Okay, and you can add that. There's another penalty there, but it's actually a good problem for a statistician to tell us how we should be doing this. When we don't know, we have to use the same data to estimate delta E, sigma, and other things too. So anyway, so this is what we use. And so, I like using the Monte Carlo because I don't have to worry about time steps and ergodicity and so forth. I mean, like any metropolis, you can make any kinds of moves you want. You can take a molecule and rotate it, and you don't have to wait for the dynamics to do it. I thought I was going to, okay, I guess I missed the slide. Okay, and so finally, I guess we have 5 minutes, okay. We calculate forces because I'm going to talk about machine learning in a second. And this is something that Shiwei and I developed a while ago. This is a cheap version of forces. It's very simple, but basically this is the Hellman-Feynman forces, which is exact if your electron density is exact, which we hope a reptation will give us. And but it has infinite variance because this is the distance between an electron and a proton, right? And this diverges and gives you infinite variance. But basically, we just filter out the region around the nucleus. We regularize it, and we can essentially do it more or less in a controlled fashion. That is, the accuracy can be as good as you want if you're willing to accept higher variance. But you have a core size, which is like 1 atomic unit. If electrons are inside there, you filter out this divergent term. If they're outside, you just use the bare potential. So it's very simple. And so in order to do this, we have to use either reptation or diffusion Monte Carlo forward walking. And here's an example we did back in 20 years ago about a hydrogen molecule, but basically in variational, this is the exact curve here, and then this is the variational Monte Carlo, and then with forward walking, you get the forces here. So now, one point is an advantage of Monte Carlo. I think this came up when, I guess, with your talk, with Brenda's talk, that is there's a big advantage to Monte Carlo. There's a lot of disadvantages, but this is an advantage. That is, extra averaging is almost free. In Monte Carlo, we're averaging over a tremendous number of variables. 3 times the number of electrons, plus the number of protons, plus the number of rotation slices. To add in a few more variables costs nothing. And the variables we're adding are K-point sampling, twist averaging, and path integrals for the ions. And so if we have typically like 10 or 20 points on our path integral, and we have typically like 100 K-points. In addition, this gives us an easy way to parallelize things. Each one of those goes into a separate process, right? And then you just average the things together, and it doesn't cost you any time because the error in the delta E, which is all we care about, is reduced by all that computational effort. Whereas in something like ab initio molecular dynamics, it would increase by this parallelization, right? So that means we lost a lot by doing Monte Carlo, but over DFT, but we gained a lot with this step. Of course, whether it's competitive or not, that's not really fair because we have a more accurate theory. Okay, so machine learning, very briefly, Ray actually a few years ago did this comparison of calculating forces, or in this case is pressures, all these different functionals. You see that they, in dense hydrogen, you see that it depends a lot on the functional. That's what these bars are. I know you can't read all the different functionals. We found that actually van der Waals things work a lot better. This is the error and the force, I guess. So our model is, I haven't done very much myself, but we use basically a 3-level model. First, we take the exact Kolo-Orniavich H2 potential. We put that in, and we start out. Then we fit the different, because we want to describe molecules accurately. Then we fit the energy of a DFT functional minus what we already had to something like DeepMD. We haven't developed our own machine learning software. We just use other people's. And then the third step is we fit quantum Monte Carlo minus DFT to another DFT. But of course, this one has a lot fewer parameters in it, the second one. So then Scott, who's here, has done a lot of this work. We made this database of forces. We have around 100,000 configurations, each with 96 protons, generated with a whole bunch of different methods. And these points here in the temperature, pressure, show you where we've computed things. We sort of tried to focus on the molecular region in this project. Okay, because I have a lot of questions about the long-range interaction when they're ionized, so we kind of stuck with when they're mostly neutral atoms or molecules. Then around 18,000 of these configurations, we actually used the calculated QMC forces with QMC pack mostly. And this is actually on this database here, required by DOE. And okay, so I think since I'm kind of out of time, aren't I? We did some, we used both the GAP software from Cambridge and also the DeepMD model from Princeton. And we compared, the usual things of how accurate are the forces, the energies, the forces, and the virials. And, they seem pretty accurate. And they seem about the same. The two things are comparable. But the DeepMD is a lot faster when you're running it on molecular dynamics. So the only thing that we've actually done is looking at the melting and the solid structures. And I showed you some of those results earlier on, but basically using about 2,000 quantum protons, we use LAMPS and IPI to compute the two phases and to compute the crystal structure. So what you do is you start out in a system which is solid and a liquid interface, and you see which one wins out, right? If you run it for a long time, does it all melt or does it all freeze? And when you have the right temperature, then it ends up, staying in equilibrium, a mixture. Okay, and so that's where we got our melting curve, and we're about to publish things. So I'll stop. Oh, I have one more thing, of course. I've done this with a lot of people. Carlo and Marcus have been with me for this whole trip for a long time, but then Paul at Flatiron has worked a lot on this, and Scott, whose picture I don't have, and Miguel Morales, a lot of other people worked on this around the world. So I'll stop there. Thank you.